Welcome to Unit 3 on trigonometric functions. In this video, we're going to tackle angles and their measures. So, being that this is the first major video over our trigonometric function unit, we should probably talk about what trigonometry is. So, simply put, trigonometry is the study of triangles and the lengths and angles of their sides. Triangles have three sides, three angles, so really understanding those three sides and those three angles and the relationship is really a big chunk of what trigonometry is all about. And that should be pretty easy to understand. Triangle starts with TRI, trigonometry starts with TRI, so it makes a connection as to why trigonometry does an awful lot with triangles. Now, as one of the most important fields of mathematics, particularly for careers that are built around calculating angles, a working knowledge of trigonometry and its uses is super important for students of all ages. All right, now, as we begin our conversation about trigonometry, lengths and angles of sides, we need to talk about the problem of angle measure. Now, you might be like, I didn't even know there was a problem of angle measure. Well, there is a big problem of angle measure. And here's why. The input value in a trigonometric function is an angle measure. So there are 6 trigonometric functions, and hopefully you somewhat know them: sine, cosine, tangent, cosecant, secant, and cotangent. Whether you know them or not, you're going to learn a lot about them here in the short future. But the idea is that the input values of all 6 trig functions is an angle measure. An angle goes into all of the trig functions, and the output is a real number. So believe it or not, this actually poses a big problem for us if we choose to measure our angles in degrees, which honestly we often do. So the problem is that degree units have no mathematical relationship whatsoever to linear units. The angle, for example, 5 degrees, it's like an arbitrary value. Like you can get a protractor to understand what 5 degrees looks like. You can even draw a little angle that measures 5 degrees. But that 5 degrees has absolutely nothing to do with any type of linear unit, which makes it kind of like really just random. Like, we know that there are 360 degrees in a circle of radius 1, but there's also 360 degrees in a circle of radius 100. Any circle, no matter how big or how small, has 360 degrees in it. And, that makes it almost kind of arbitrary. Like, who came up with 360 degrees? Like, why don't circles have 500 degrees? Or why not make it a nice 1,000 degrees in a circle? So it's really just this arbitrary unit of measurement that, just has no connection to any kind of relationship for how that angle was created. And that makes them really kind of poor to work with, even though we do work with them a lot. In fact, most of you are very familiar with degrees. So the 360 degrees has no relationship to the radius. So the number 360 and the radius of a circle have nothing in common. Now, you might think, well, wait a minute, why are you bringing a radius into this? Well, okay, let's talk about that so we can understand that clearly. So let's consider the following 2 pictures. The first picture on the left here is a triangle, right? Trigonometry all about triangles. And we have an angle labeled right here, theta. Now, just so you know, a circle like this, with a little line through it, that is the Greek letter theta. And the Greeks really started a ton of this investigation into triangles and their angles, and really started trigonometry. So we often label angles with Greek letters, like theta or alpha is another one, or beta. Now, you don't have to use Greek letters. We just typically do, but you don't have to. You could call an angle X or W or Q for all I care, but we typically do use Greek letters since they kind of founded all of this stuff. Great, wonderful, doesn't matter. So I have this angle theta, and across from it is a length A and a hypotenuse H, right? And, we could call the other base down here B, whatever. You guys are very familiar with Pythagorean's theorem, A squared plus B squared equals H squared. Okay, awesome, fantastic. But that angle theta has literally nothing to do with the H, the A, and the B. Literally nothing. If I were to make this triangle bigger, extending the hypotenuse, which would make that far leg bigger, which would make the bottom leg bigger, that doesn't change the angle. The angle theta is still the angle theta. So again, there's just no connection there whatsoever. And that's what kind of makes angles, measuring in degrees just not really that fun. It's actually a lot more natural to think about an angle in terms of the arc it creates. So imagine if the hypotenuse was the radius of a circle, right? So if this was the center of the circle down here where the angle is located, and if the hypotenuse was the radius and I swung that hypotenuse around, I'd create this ginormous circle. Okay, Well, it makes a lot more sense to reference that angle theta having something to do with the arc it creates. So you notice that if this right here is the radius and this right here is also a radius, then we have an arc that gets created. And we typically call arcs S. I don't know why, we just typically do. Again, you call it really anything you want, but typically we call the arc length S. It's an arc. And it makes a lot more sense, right? It's a lot more natural to think of an angle being determined by the arc rather than the arc being determined by the angle. So this angle and this arc and the radius actually have a lot in common. Because if the radius is smaller, then the arc's going to be smaller. If the radius is bigger, then the arc's going to be bigger. So connecting the radius to the arc to the angle actually makes a lot more sense. And this connection between the radius, the angle, and the arc created inspired radian measurement of an angle. Radian measurement is another way to measure an angle that makes a lot more sense. Now, this doesn't mean we're going to put degrees to the grave. We're still going to use degrees, in fact, quite a lot, because they are so common in the real world. But radians is a much better way of measuring angles. So let's talk a little bit more about measuring in degrees. Before we move any further with radians, let's talk about measuring with degrees. Of course, angles can be measured in degrees. I don't want you to get convinced that I'm never going to measure angles in degrees. We will definitely use degrees many, many times, and you're going to see them pop up throughout this entire unit. But I want to make it clear that, degrees are very useful. I don't want you to think that I'm, again, burying them in the grave. So, for example, here's one particular use of angles that we do see a lot in navigation. Navigation by boat, airplane, or even traveling by car. In navigation, the course or bearing of an object is given as the angle of the line of travel measured clockwise from due north. So, for example, if here is a boat in this particular city right here, and it's going to leave port, and it's going to leave at a bearing. Okay, we call that a bearing. And its bearing is the number of degrees clockwise from due north. So obviously you guys all know due north is straight up. So again, if I'm going at a bearing of 155 degrees, that means I'm going at 155 degrees from due north. And again, that's not counterclockwise, that's clockwise. Okay, so you're like, what does this matter? Well, this is actually going to come in handy big time. Just understand that navigation, a bearing is the number of degrees a particular object travels from due north, clockwise from due north. So I'm not going to do any more with this navigation idea right now, but I'm just bringing it up to give you guys a point that degrees are used in the real world a ton. So I don't want to completely get rid of them, but they really they don't have a lot of understanding or relationship to them, whereas this new measure of angles, radians, does. So let's talk about radians. Radians are the preferred measurement of angles in the mathematical world. So I am going to use them a lot, even though I'm still going to use degrees. I got to be fair. So what the heck is a radian? So a central angle of a circle has a measure of 1 radian, or we just say rad for short, because they're pretty rad, if the angle intercepts an arc with the same length as the radius of the circle. And for some kids, that's just mind-blowing to comprehend. So let's just really take this time slowly. So if I'm measuring this angle right here, and I'll just call it theta again. If I'm measuring this angle theta, obviously I could pull out a protractor and measure it in degrees, but I don't want to use degrees anymore because, again, like I said, it's a problem. It doesn't have any connection. So here's the deal. As I swing my length, so if I take the bottom edge of my angle and I start to swing it up, and every time I swing it up more and more and more, the angle gets bigger and bigger and bigger. When the length of that arc equals the length of my radius, I have 1 full radian. So that's why radians are awesome, because they directly connect the length of the radius to the length of the arc. So once again, if I were to get out a piece of string and lay it from the center of my circle all the way to the edge of the circle, and then I take that 1 radius, and then again, imagine it's a piece of string, and then I were to lay that piece of string out on my arc. And again, when you lay the piece of string on an arc, you kind of curve it a little bit. And where that piece of string ends is 1 full radian. So that's the definition of what a radian is. A radian is the direct relationship between the arc length, which we typically call S, and the radius, which we typically call R. And when the arc length S equals the radius R, we officially have what is known as 1 full radian, or RAD for short. So radian measurement is simply the ratio of an intercepted arc length divided by the radius. So a radian measurement is the ratio of the intercepted arc that the angle creates divided by the radius. And again, check this out. When the intercepted arc equals the radius, you're going to get 1. So if the radius is 16, then when the arc is 16, 16 divided by 16 is 1 radian. Or if you have an enormous circle that's 1,000 feet wide, or I'm sorry, 1,000 feet is the radius, well, when the arc length is 1,000 feet, you're going to get a radian of 1. 1,000 feet for the arc, 1,000 feet for the radius, divide, you get 1. So that's what a radian measurement is. Get used to that formula. A radian is the arc length S divided by the radius. So here is that formula. And I just wanted to be very clear on this formula. So an angle, again, we typically call theta, but you can call it whatever you want. Theta in radians, right? Be very clear, this formula is for radians. Theta in radians is the arc length divided by the radius. Now, there's no units for radians. They're just radians. The unit is radians. And that's because they're two lengths. So if we have an arc length that's measured in feet, and then we have a radius that's measured in feet, then those feet cancel out, and that's why there's no unit. There's no length unit. It's just radians. Now, this is better, right? Why are radians better? Because they take into account the relationship between radius of a circle and the length of a created arc. So if I say, hey, draw me 50 degrees, you're just going to pull out a protractor to know where 50 degrees is. There's no understanding of where that 50 degrees came from. But a radian, there's a lot of understanding. So again, if I were to say, hey, draw me 2 radians, where's 2 radians? Well, you would say, okay, here's my length of my radius. And I could get out a ruler and measure that length of that radius. And then I could lay that radius out on my arc. And maybe there's 1 radius. And maybe here's 2 radiuses. So where I have 2 radiuses equal to my arc length, then that's where I have 2 radians. So there would be roughly 2 radians. So hopefully that picture kind of makes sense. But this formula is really the big formula that you need to know for what radians are. It's the arc length divided by the radius. So again, every time you create a arc length that's equal to your radius, you've created 1 radian. So even if we wanted to do a half a radian would be your arc length equals half of the radius. So if you figure out what half of the radius is and lay that out right here, boom, there is a half a radian. So again, it's just a much better way of measuring angles because it connects the radius to the arc length created. All right, now this formula also brings apart another formula, right? We spent a lot of time with formulas recently. So theta in radians equals the arc length divided by the radius. So if I simply multiply the r over, just by doing some simple algebra, I get that the arc length equals r times theta. So again, this is also true, right? So again, there is an awesome relationship between these 3 values. All 3 of these values are clearly connected. And that's what makes this such an amazing formula, is that you could solve for any one of those variables. Now, the key thing you do have to constantly remember is that if you are going to use this formula, theta cannot be in degrees. We're not talking about 50 degrees or 25 degrees. We're talking about radians. It's got to be measured in radians. So let's dive a little bit more in how they are connected. Because as much as I'm saying that there's a problem with degrees, there is a direct relationship between degrees and radians. There really is. So let's look at a full circle. So if I were to ask you how many degrees in a full circle, everybody and their brother is going to say 360 degrees, right? Everybody knows that. It's just something you've been trained to know, even if you have no idea where 360 came from. And again, that's the problem with degrees, is we have no idea where it came from. We just trust it. But now let's talk about radians. How many radians are in a full circle? Well, remember, a full circle is a circumference, right? Okay, so if the arc length of a full circle, the arc length, if I were to go all the way around, the arc length is the circumference. And the circumference of a circle, I'm sure you guys all know, is 2 pi r. Or at least you could Google it if you don't know. So a full circle is 2 pi r. So if I said, how many radians are in a full circle? Well, again, radians is equal to the arc length divided by the radius. So in this arbitrary kind of just random circle here, the full circle, all the way around a circle, is the circumference, 2 pi r. And the radius is, well, it's the radius. So if the radius was 16, then the circumference would be 2 pi times 16. If the radius was 9, then the circumference would be 2 pi times 9. So here's the great part, is that those radiuses cancel. Whether they're 9 or 16 or 5 or 10, who cares? Their radiuses cancel, and you get that there are 2 pi radians in a full circle. Now that makes a lot more sense, right? Like, again, if I told you to write a book on why 360 degrees are in a circle, you wouldn't have any idea why to write that book. But if I said you explain to me why there's 2 pi radians in a full circle, we can actually make connections. It's the arc length of an entire circle, 2 pi r. The circumference of an entire circle, 2 pi r, divided by the radius. And that allows the r's to cancel, so there are 2 pi radians in a full circle. So 360 degrees equals 2 pi radians. So this is a conversion factor, right? It's almost similar to, hey, 12 inches equals 1 foot. There is no world where 12 equals 1. Please, 12 does not equal 1. But the moment you put units on there, 12 inches does equal 1 foot. So this is very much like that. It's a conversion factor. 360 degrees, even though we don't know where that comes from, okay, we know there's 360 degrees in a circle, 360 degrees equals 2 pi radians. And I can actually simplify this because both sides are divisible by 2. So just to make it a little bit simpler, there's 180 degrees equals pi radians. So that's just a little bit better conversion factor. So in a half a circle, 180 degrees, that is equal to pi radians, okay? So hopefully that makes a little bit of sense. And the other thing you got to understand is that, because circles involve pi, it's irrational, right? So there's not an exact number of radians the exact number of radians in a full circle would be 2 pi, but approximately, 2 pi is about 6.28. So, but again, there's more decimals there. That's an approximation. So we know that a full circle is 360 degrees. A full circle also has 6.28, exactly 2 pi radians. So you could use either one of these conversion factors here, but this bottom one is just more reduced. All I did was divide both sides by 2. So now using this conversion factor, I can actually convert radians into degrees. I could take something measured in radians, convert it to degrees, or vice versa. So if you are measured in degrees and you want to get radians, then all you got to do is multiply by pi over 180. Again, that's the conversion factor, right? Pi radians equals 180 degrees. So that's a conversion factor. So I know that pi divided by 180 is not 1, but technically with units it is 1. Pi radians over 180 degrees. Pi radians is equal to 180 degrees. So essentially, this is multiplying by the number 1. Just like if you're converting between feet and inches or even minutes and seconds. If you're in radians and you want to get to degrees, you multiply by 180 over pi. Pretty simple. Remember, that's pi radians. Oftentimes we do put the RAD, but if you don't put it, then it's just implied that it's radians. We always use the degree symbol, the little circle for degrees. But if it's in radians, oftentimes we just don't put anything because, again, like I said, technically the units cancel out and there really are no official units of radians. We just call them radians. So these are very, very simple conversion factors that are very, very easy to use. Let's just demonstrate how easy this is to use. So let's convert these 3 degrees to radians. So these are all in degrees. Sorry, my computer didn't have that little circle, so I just wrote degrees. But these are all in degrees. Let's convert these degrees to radians. So again, when you're converting, if you want the degrees to cancel, they need to go in the denominator. So I'm going to put the 180 degrees in the denominator. That way the degrees cancel out. And I'm going to put the pi radians on top. Now, when I go to my calculator, if I enter in the pi, I'm going to get an irrational number that is impossible to simplify. So I'm going to hold off on the pi. Just like when I eat dinner, I always hold off on my pi until after dinner. Very bad discussion there, I know. So anyway, so I'm going to take 90 and I'm going to divide it by 180. I'm not going to enter the pi in because the moment I enter pi in my calculator, I can't go back to a fraction. It's going to be an irrational number. So it's 0.5, or if you didn't know how to do this, this is awesome. If you hit math and then fraction, it's going to take your previous answer and make it a fraction. So 90 divided by 180 is 1/2, but don't forget you got to put the pi back on. So it'd be 1/2 pi radians, or 1 times pi is pi, so we can just put pi over 2 radians. So 90 degrees is equal to pi over 2 radians. Two different measurements for the exact same thing. All right, let's do 75 degrees. Once again, I'm going to multiply by pi over 180. I put the 180 in the bottom because I want the degrees to cancel. And then again, I'm going to go to my calculator. 75 divided by 180 equals, again, if you don't know what fraction that is, use the math fraction button, change it to a fraction, 5/12, and then put the pi back on. 5/12 pi. Let me just show you real quick what happens. If I take that 5/12 and times it by pi, again, I get an approximation. So 5/12 pi is approximately 1.31. But again, I don't like approximations. I like exact answers, so I'd much rather the 5 pi over 12. But again, 5 pi over 12, 75 degrees would be 1.31 radians. So if you want to put 1.31 radians, if you're allowed, that's fine. So actually, let's kind of look at that to make sense of this, right? So here's a full circle. 75 degrees is roughly somewhere around here. Roughly somewhere around here is 75 degrees. And that would be equal to 1.31 radians. Now, what does that mean realistically? Well, here's my radius. Here's one radius. And I need 1.31 radians. So if I lay this out, I'm going to get one full radius, and I'm going to get this little bit extra. That little bit extra is the 0.31. So 75 degrees is 1.31 radians. But again, the 1.31 is not exact. That's why I'd rather say 5 pi over 12, which is exact, but equivalent to 1.31. Now let's do one more here, 415 degrees. Once again, if I want to convert this to radians, I'm going to put the pi on top. I'm going to put the 180 degrees in the bottom because I want the degrees to cancel. I'm going to go to my calculator, and I'm going to type in 415. I'm going to hold off on the pi, divided by 180, and I get 2.315, 2.31 if you round. But again, remember, math, fraction, we love exact answers. Come on. 83 over 36, crazy number, but it is what it is. 83 over 36, but then don't forget to put the pi back on. Now, once again, you could always multiply the pi on the calculator, but you're going to get an irrational number that might make it understandable to look at and graph and understand, but we like nice exact answers. All right, now let's go backwards. This time, let's convert from radians to degrees. So this time, we're going to start off with pi over 3 radians. Now, I'm going to multiply this to convert it. Well, this time, I want the pi radians in the bottom because I want the radians to cancel, and I want the 180 degrees on top. So I want the radians to cancel. That way, I could be left in degrees. So now this is super nice, is that the pi's cancel. So now I don't have to worry about the pi's. They literally go away. So I have 1/3 times 180. So I'm going to type in 1/3 on my calculator. There's the 1/3, and I'm going to times it by 180. Another way you could do that is use a parenthesis, 1/3 times 180. And you say, well, where'd the pi's go? Well, they canceled out. Man, whatever. That's great, right? So that's 60 degrees. So 60 degrees is pi over 3 radians. All right, let's do 3 pi over 5. Once again, 3 pi over 5 is in radians. So I'm going to multiply that. I'm going to put the pi radians in the bottom. That way the radian measurement or the radian unit cancels. 180 degrees on top. The pi's cancel, which is an added bonus. I'm going to go to my calculator. 3/5 times 180 equals 108 degrees. Awesome, easy. All right, now this time it's 3 radians. And you say, well, where's the pi? Okay, radians don't have to have pi, right? So again, imagine if you have a circle of radius 1. Radius is 1. When you have one arc length, there's 1 radius, and here's another 1 radius, and here is another 1 radius. So that's where you have 3 radians, right? If your arc length is equal to 3 radiuses, you have 3 radians. So you don't have to have a pi in your answer. So 3 radians. So once again, I still want the pi radians in the bottom because I want it to cancel out. And on top, I have 180 degrees. All right, so if I multiply this, I'm going to do 3 times 180. Again, I can't cancel out the pi. The previous two problems, the pi did cancel. Here, the pi doesn't cancel. So I'm going to go to my calculator. 3 times 180 is 540. So the exact answer would be 540 divided by pi degrees. Now that's kind of hard to think about. So sometimes when we're in degrees, it's much better to, like I said, I don't want to type the pi in, but sometimes it's useful to understand a little bit more what that value is. So that would be about 171.887 degrees. So roughly 171.887 degrees. So that'd be a rough equivalent there of how many degrees that is. All right, so those problems hopefully are pretty easy. Let's take a look at a couple more. Find the length of an arc intercepted by a central angle of 0.5 radians in a circle of radius 5 inches. These problems can be a little bit tricky. I highly recommend drawing a circle. It will always help. So if I draw a circle and it says the radius is 5 inches, I'm going to put a 5 right there. It says find the length of an arc intercepted by a central angle of 0.5 radians. So maybe you don't know where 0.5 radians is. It doesn't even matter if you're right or wrong. You're just trying to draw a picture to get a rough idea. So even though that might look like 90 degrees to you, who cares? You're just trying to get a rough idea. And they want me to find the arc length. So I know the radius. I know the angle in radians, 0.5 radians, and I'm trying to find the arc length. So again, remember the formula. Theta in radians equals arc length divided by radius. So all you gotta do is fill in the blanks. The angle is 0.5 radians. I don't know what the arc length is. I do know the radius is 5. So all I gotta do is multiply both sides by 5 and I got myself the answer. 5 times 0.5 is 2.5. So my arc length is 2.5 inches. And that actually makes complete sense. Think about that for a second. Remember, radians, 1 radian is when the arc length equals the radius. So a half a radian would be when the arc length is half the radius. Ooh, seen a connection here? 2.5 is half of the radius. Now that means my picture is really not drawn to scale at all, but that's because I didn't know going into it. If I want to draw this a little bit better, if that's 5, then I need half of that distance to be my arc length, and maybe somewhere right around there would be a little bit better interpretation of 0.5 radians. All right, so another one. Find the radian and degree measurement of an angle that intercepts an arc length of 10 inches in a circle of radius 4 inches. Once again, pictures always help, even if they're not drawn perfectly. All right, the radius is 4 inches, so I'm going to go ahead and mark my radius here as 4 inches. And the arc length, so I have an angle, the arc length is 10 inches. Once again, I don't know exactly where this angle is, but I don't really care for the sake of my picture. I just want to make sure I get an understanding of what's happening here. And they want me to find this missing angle, I'll call theta. And we know that theta equals the arc length divided by the radius. So I'm just going to fill in what I know. The arc length is 10, the radius is 4. Boom, the angle is 10/4. 10 divided by 4 is 2.5. So this angle is 2.5 radians. Please make sure you know that it's radians, radians, radians. Anytime you use this formula, you're in radians. Now the question did say to also find degrees. So now let's go ahead and do the converting. So we're going to do an extra step here. 2.5 radians. If I want to convert this, I want the pi radians on the bottom. I want the 180 degrees on top. That way my unit of measurement radians cancels. So now I'm going to go to my calculator. This is 2.5 times 180 divided by pi. So there it is, 2.5 times 180 divided by pi. And again, I am putting pi in here because when we want degrees, typically we don't give degrees in terms of pi. That just doesn't make a lot of sense, but we do give radians in terms of pi. So anyway, 143.239 degrees. So we're at a roughly 143.293 degrees. So that's the rough angle. 2.5 is the exact radian measurement, approximately 143.293 degrees. All right, let's do another one. Find the perimeter of a 60-degree slice of large 7-inch radius pizza. All right, so we got a big old slice of pizza here. We love the slice of pizza. Here it is. Got some pepperoni on it. It's got some mushrooms on it. It's got some cheese. Okay. What we want to do is we want to find the perimeter. The perimeter is all the way around the outside, not just the arc, right? All the way around the outside is the perimeter of a piece of pizza. So the good news is we know that it's a 7-inch radius large pizza. So that means we know that this distance right here is 7 inches. And, you know, both straight sides of a piece of pizza are the same as long as you cut it correctly. So those are both 7. So we got to figure out the arc length. So we know that this is 60 degrees because it said it was a 60-degree slice of pizza. We need to figure out the arc length. Oh, this is great. I got a great formula. Theta equals arc length divided by radius. Okay, fill in all the blanks. I'm looking for the arc length. That's what I want to find, S. I know the radius is 7. This is all easy. But here's the problem. Don't you dare put 60 degrees right here because this is in radians. Got to be in radians. If you're going to use this formula, it's all about radians. So I have to take a hot break, hot timeout, and I got to convert 60 degrees to radians. So we know that I want the 180 degrees in the denominator. I want the pi radians on top. And I'm going to hold off on the pi, and I'm going to do 60 divided by 180. And sometimes you might know that off the top of your head. But anyway, 60 divided by 180 is, I'm sorry, I typed in 6, brain fart. 60 divided by 180 is 0.33, which everybody recognizes as a 1/3. So we got 1 pi over 3 or pi over 3. So that's what I'm going to put in right here because I want it to be in radians. Got to be in radians if you can use this formula. All right, now I got to solve for S, which I could actually just cross multiply. 7 pi equals 3S. Divide both sides by 3. So the arc length is 7 pi divided by 3. Now you might say, well, wait, isn't that radians? No, just because there's a pi, that could be in inches, right? Pi is just a number. So, you know, it's an arc length. It's not always going to be perfect. What are you going to do? Sometimes you measure something, you know, think about measuring a piece of string. Is it always going to be a whole number? No, you sometimes get decimals. So if you want to approximate what that is, we would type in 7 pi divided by 3. So that's the crust. The crust is 7.33 inches long. Add the two other sides because they want us to find the perimeter. That's the 7 and the 7. And we get 21.330 inches is the perimeter all the way around that slice of pizza. So pretty good problem, pretty easy problem, but you really have to remember if you're going to use this awesome formula, you got to make sure you're in radians for all problems. All right, let's keep going here. Find the radian and degree measurement. Oh, we already did that problem. Sorry, that was a repeat. Should delete that. My fault. All right, here's the other one. All right, in a circle, an angle measuring 4.9 radians intercepts an arc of length 3.4. Find the radius to the nearest tenth. All right, some kids right away get confused. Draw a picture. It always helps. So we have, we have an angle. And if you don't know exactly where 4.9 radians is, who cares? Just make it approximate. It doesn't have to be perfect. So just draw an angle, right? Look how ugly that is. Doesn't matter. There's an angle, 4.9 radians. And the intercepted arc, the arc that gets intercepted by that angle is 3.4. All right, find the radius. Okay, well, once again, I know a great formula. Theta equals S divided by R. All I got to do is fill everything in. The arc length is 3.4. I'm looking to solve for the radius, and the angle needs to be in radians, which it is. It is in radians. That's a good thing. So 4.9. Now all I got to do is cross multiply to solve. So I get 4.9 R equals 3.4. That's easy math. So R equals 3.4 divided by 4.9. Use a calculator, obviously, unless you can do that in your head. And you get 0.69. It says round to the nearest tenth. So it'd be 0.69, but that would actually round to 0.7 if we were going to the nearest tenth. That's it. I mean, how easy was that? Draw a picture. Always helps. Use the formula. It always helps. Let's just do one more final problem. In a circle of radius 2, an angle measuring 3 pi over 4 radians intercepts an arc. Find the length of the arc in simplest form. All right, once again, if you're ever confused, draw a picture. It always helps. We were told the radius is 2. There it is, 2. And again, the angle's 3 pi over 4. Who cares? It's just a picture, guys. I'm not going to judge your picture if you don't put it in the right spot. So just draw a random angle and label it as 3 pi over 4. Even if it's not correct, you're just trying to get a rough idea of what's happening. And they want me to find the length of the intercepted arc, and that is S. So theta equals S over R, fill in the blank. I don't know what S is. I do know the radius is 2. And again, just make sure that this value has to be in radians, which it is, so I'm safe. 3, if it was in degrees, I'd have to convert it, that's all. So 3 pi over 4. Now I'm going to go ahead and cross multiply. I get 4S, that's an S, not a 5, equals 6 pi. So S equals 6 pi over 4, which you could reduce to 3 pi over 2. Now this is a length, so I would have no problem. You know, I like exact answers, so obviously the exact answer is 3 pi over 2. But you could certainly type this into your calculator if you want to get an approximation. 3 pi over 2 is about 4.71. So this is approximately 4.71. But this right here would be the exact answer in simplest form, but it's approximately 4.71. So the length of that arc would be 4.71. And again, this would be true if it was in miles, inches, feet, millimeters, doesn't matter, whatever the unit is. This problem didn't necessarily specify units, so I'll just leave it as no unit, even though there should be a unit there. Units, whatever. Radiuses and arc lengths do have a unit of measurement, whether it be feet, miles, millimeters, centimeters. This problem just didn't specify, no big deal. All right, guys, that's it. Hopefully this first video for trigonometry, I know it's a long one, but there really is a lot of information here that's super important for you to process and understand. But at the end of the day, it's really all about this new unit of measurement that takes an old unit of measurement that's just honestly a little bit outdated, even though we still use degrees all the time. Radians is really a much better way of measuring angles because it just makes more sense in terms of relating the arc length to the radius. All right, that's it. Be ready to roll for the next video.